Okay, so now we know what's linear relaxation. Now we want to see what's the relationship between that linear program and our original integer program. So there is a fact that is useful. For minimization integer program, its linear relaxation always gives us a lower bound of its objective value. So more precisely, let's see what's this. Suppose we have a minimization integer program, and once we find its optimal solution, we may get its objective value. Let's call it z star. So z star is for that integer program, okay? And we also have its linear relaxation. So we make its linear relaxation. We may also solve that linear program and get its objective optimal solution with objective value. Let's call it z prime. Okay? Then the fact is that z prime is going to be less than or equal to z star for minimization problem. Okay? Why is that? Well, it's actually very easy. So suppose we are comparing these two programs. This is an integer program. This is a linear relaxation. They have the same objective function. Moreover, the linear relaxation's feasible region is typically larger than the original integer program. Okay, here you have a larger feasible region because you are allowed to take fractional values. So if you are having a same objective function with a larger feasible region, naturally you will do better. And for minimization problem, better means less than or equal to. So that's how our z prime may be a lower bound of z star. Okay? So somehow that means, well, if I give you an integer program, if you don't know how to solve it, at least you may solve its linear relaxation. And then you will get some kind of estimation about your z star. You don't know how to get z star. You don't know what's the value of z star. But z star cannot be that small or that large. Okay? So if that's a maximization problem, then it's the other way. Linear relaxation will give us an upper bound. So you will later see this is very useful. Okay? So linear relaxation, it gives us a bound. That's good. But actually, if we are lucky enough, the linear relaxation may either be infeasible, unbounded, or give us some other solutions. So that is some cases when we have an optimal solution which is feasible to the original integer program. So in all these cases, we may say the original problem has been solved. Suppose our linear program is infeasible, then of course the original integer program is also infeasible. Suppose our linear relaxation is unbounded, the original one would be also unbounded. So both are conclusions. If an optimal solution to the linear relaxation is also integer values, it happens that all its solutions are integers, then in that case, that would also be an optimal solution to the original problem. Why is that? Well, let's take a look at the formal statement. Let's say x prime is an optimal solution to the linear relaxation of an integer program. Suppose the x prime is feasible to the original IP, which means all its values are integers. It would also be optimal. So this actually is a very general situation. Suppose you originally has a program where the feasible region is here. Okay? You don't know how to solve this one, so you relax the program and get a larger feasible region. Okay? And then you solve the relaxed program. If you see an optimal solution is here, it is not feasible to the original one, then it's of course not optimal. But if you see your optimal solution is here, is feasible to the original problem, then naturally it's optimal. Because you are selecting a solution in a smaller set, and you happen to select the same value, then naturally, if all the solutions in the yellow region cannot be greater than or cannot be better than this one, then all the solutions in the blue and in the red region cannot be greater than this one. So that's the idea. So very quickly, let's see. Suppose X prime is not optimal to the IP. There must be another IP feasible solution that is better. But if X prime prime is IP feasible, then it would also be feasible to a linear relaxation, and then your X prime certainly cannot be optimal to that. So they are talking about the same thing, just in an algebraic way or graphical way. But now, even though we have these lucky cases, we may still be unlucky. And actually, most of the time, we are unlucky. We solve the linear relaxation, get a solution, and there are some fractional values. So in that case, naturally, we may think, oh, how about this? Let's round up or round down the fractional values to get integer solutions, all right? So let's say we solve a linear relaxation and get a solution X prime. Sometimes we say this is LR optimal. LR means the linear relaxation, okay? So LR optimal means X prime is optimal to the linear relaxation. However, we see at least one variable violating the integer constraint. So it may be 3.2, it may be 0.8. It's not IP feasible. So it's not IP optimal. Then let's say we want to round the variable. Then the question arises, do we want to round up? Do we want to round down? There must be some way to tell and to do this decision. And the resulting solution, is it always feasible? Probably not. And will the resulting solution be close to an IP optimal solution? Well, there's no way for us to tell. So here, let me give you an example. Suppose you have an IP which is here. So the objective constraint, they look very typical. You have integer variables, and they should be non-negative. So once you take a look at all those integer points, okay, all those integer points, you will see that the optimal solution is this one. The optimal solution is 5, 0. And once we have that, now let's take a look at LR solution. LR optimal is to solve this linear program, which is the shaded area here. All right? And if you do that, very quickly you would see that your optimal solution is 15/4 and 9/4. The interesting thing is that if you do round up for both variables, your solution is not feasible. Okay? And you may see that's true because these are less than or equal to constraints. You cannot just round up two variables. If you round up one solution, for example, round up x1, you're going to get 4 and something. But then you may see that the 4 too is also infeasible. Okay? So that's also not a very good idea. Also, if we are talking about the other solutions, none of these are optimal solutions. Our optimal solution is 5, 0, which is somewhat far from our x1, far from our LR optimal solutions. So that means if you round up or round down, that may create infeasibilities. Okay? In this particular case, if you round up just one variable and keep the other variable unchanged, you're going to be here, or if you round up both, or if you round up just one of them and round down the other way, there are so many possibilities for you to get infeasible points. And even if you try all the integer solutions be around your fractional solution, you still don't get an optimal solution. So that means solving a linear relaxation and then do rounding is not a general strategy. We need some more, and that would be branch and bound.